Okay, let's go ahead and continue with example 14.5. Remember we were looking at a styrofoam ice box with some area and thickness, and we want to know how much ice melts in a day if the ice box is kept in a trunk of a car. Okay, so we're looking at, I'm going to quickly kind of draw this ice box, right? And inside has a temperature T1, and on the outside there's a temperature T2. Okay, that's going to be the higher temperature. So T1 is equal to 0 degrees. T2 is 35 degrees. Okay. We also have our thickness, D, is 2.5 centimeters, or I can go ahead and convert that to meters here. Okay. And we have our area is 0.95 meters squared. Okay. So this is what we know. We also know the time that the box is in the trunk of the car, and that is 1 day. And we know that we need to convert that into seconds, so let's go ahead and do that real quick. So in 1 day there are 24 hours, and in 1 hour there are 3,600 seconds. Okay, so our total time is 86,400 seconds. Okay. All right. So, we will be using our equation that we just learned. So Q over T is equal to Ka times T2 minus T1 over D. Okay, we also want to note that our heat to melt the ice is going to be equal to the melted ice mass, M, times our freezing point or melting point, latent heat. Okay, coefficient here. So my mass here is going to be what we are looking for. So we're saying how much ice melts in 1 day. So we want to know some kind of mass in 1 day. Okay, so what we will do is rearrange these, okay, and solve for Q here, and plug this into here. Okay, so first I'm going to say mass is going to be equal to Q over LF. And then I'm going to say M is going to equal to Ka times T2 minus T1 over D. We would multiply our time over, okay, and then we still have divided by LF, so I'm going to just put that here. Okay, so this is our equation that we'll be using. And so all you have to do now is plug all of our values in and solve for our mass. Okay, you could have done this in steps. You could find Q first, you could find Q over T first. It's really up to you. I think messing with the equation is easier than messing with a bunch of numbers first of, like right off the bat. So this is how I like to do things. Okay, so let's look at a couple things. So we need to find our K for styrofoam, and that's going to be in the textbook. We need to know our L sub F for ice, and let's see what that is. We did use that previously, so LF is equal to 334,000 joules per kilojoule. Whoops. And so we just need to find our K. Let me show you where that is in the textbook. Okay, so we're going to go to conduction. Okay, so here it is in this table, 14.3. And again, we're looking for styrofoam. So this is going to be our substance and our thermal conductivity. Okay. So we're going to scroll down. Styrofoam is the very last one. Whoops. So it's 0.01, and that is in joules per second meter degrees Celsius. Okay. So 0.01 joules per second meters degrees C. Okay, these units are kind of funny looking. Okay, so let's go ahead and plug everything in. Times our area, 0.95 meters squared. Times T2, which is the hotter, that's going to be 35. T1, the cooler, divided by our thickness, 0.025. Our time is going to be 8,600 seconds, and L sub F is 334,000 joules per kilogram. That should, wait. Yeah, kilogram. I think I messed up. Okay. So then we can plug this all into our calculator, and we'll get a value of 3.44 kilograms. So this is the mass of the ice that melts. So 3.44 kilograms of melted ice. Okay. All right, let's go to our next example. Okay. Water is boiling in an aluminum pan placed at on an electrical element on a stove top. The saucepan has a bottom that is 0.8 centimeters thick and 14 centimeters in diameter. The boiling water is evaporating at a rate of 1 gram per second. What is the temperature difference across the bottom of the pan? Okay, so we're looking for some kind of delta T here. Okay, I like to write down what I want to know first. Okay, looking back at our equations, here, delta T is this T2 minus T1, okay? And so we want to know that temperature difference here. So we can rearrange this equation quite simply, okay? And find our delta T. So I'm just going to go ahead and write that. Delta T equals Q over T times D over Ka. Okay, so this is our equation. Now we do, let's see, evaporating rate. We do have a phase change going on here. So we will need to know my Q of that evaporating water. Okay, so that's going to be M times L vaporization. Okay. And then from there, let's see. We can find this. Yeah, so we first want to figure out Q here. So my mass, let's see. The mass of my water evaporating at this rate. I'm going to take 1 gram. We're going to convert it. So we're going to take 1 gram of water and multiply it by our LV. So that's 2,256 times 10 to the third joules per kilogram. So that's going to be my Q. So 2,256 joules. Okay. The boiling water is evaporating at this rate here, so we're going to use that information. Since the 1 gram melts in 1 second, and we just used 1 gram of substance, okay, we're going to say that Q over T is going to be 2,256 joules for 1 second. Okay, again, we used 1 gram as our mass. Okay. Then we can just plug that in to our delta T. So 2,256 joules per second times D, which is our thickness. That's going to be 0.008 meters. Okay, that's our thickness of the pan. And K for aluminum, okay, we can go back over here and look for aluminum. It's going to be 220. That's our thermal conductivity. 220 in joules per second meters degrees C. And our area. So let me go ahead and say this is our diameter, okay? So remember that we're looking at a saucepan, so basically a circle, right? So we have our diameter, but we want to know our area. So area of a circle is pi r squared. So that'll be pi times r, which is going to be this divided by 2, okay? And we need it in meters, so let's do that, okay? So our area of this pan is 0.0154 meters cubed. I mean squared, not cubed. Sorry, area, not volume. Okay, so now once we have all of those values plugged in, we can put that into our calculator, and we will obtain a temperature difference of 5.33 degrees Celsius. Okay? All right. So now we can start talking about convection. So remember, we were just talking about conduction. That is one substance touching another substance or material. Okay, but convection is a little different. This is going to be driven by buoyant forces, okay, such as saying that hot air rises because the density decreases as temperature increases, okay? So think about, like we had earlier, that there's cool air on the bottom, and it's going to this furnace, and then this heats up, the hot air rises, and then it gets cooled off, and then it sinks, and so forth. So you get this circular motion, okay? So again, hot air is, I'm going to say, less dense than cool air is more dense. And that also applies to other things. So if you have something that's hotter, it's going to be less dense than something that's cooler, that's going to be more dense. Okay?